Happy Spring Equinox, everybody! It is March 21st, 2025, one day after the Spring Equinox, and that means the sun is almost directly overhead the equator, or in other words, the subsolar point today is almost on the equator, which means we can do some fun astronomical experiments. I don't think I could have said it any better, past Chris, even though I just did. Anyway, it's the equinox, which means the sun is directly above the equator of the Earth. Now, as you may know, because of the tilt of the Earth, the point that the sun is directly above changes throughout the year. For example, in the summer, it'll be above, the summer for the northern hemisphere, it'll be above some point in the northern hemisphere. Now, during the equinoxes, that point happens to be right on the equator of the Earth, as you can see right here. Now, let's zoom in on this image and see some of the further consequences of that fact. Okay, so here I've drawn a... That's much better. Anyway, if you draw a circle all the way around the Earth, intersecting the north and south poles and where you're standing, you get an imaginary line called a meridian. Now, you may have heard of the most famous meridian, the prime meridian, which of course represents 0 degrees longitude on the Earth. So the idea of a meridian is actually relevant to solar noon, that is, the time in the day when the sun is highest in the sky. What time is that? It's simply when the subsolar point, that is the point over which the sun is directly ahead, is on your meridian. So for example, it may be here one day. I believe this would be in the winter for the northern hemisphere. Now, if the sun were over a different point, not on the meridian, then it will be slightly angled in the sky and not as high as it could be. So, solar noon is when the sun is on your meridian. Now, during the equinox, the subsolar point is, well, of course, it's not going to be exact, unless it's at the time of the equinox exactly, which is a very specific point in time. It'll be roughly above the equator. So, if you wait for the time when the subsolar point is on your meridian and as close to the equator as possible, then a very special set of conditions will be satisfied. By the way, the reason in the last illustration I didn't draw the tilt of the Earth is because on the equinox, it doesn't matter anymore. If the sun is shining directly over a point on the equator, then no matter the tilt of the Earth, it will still be shining over that exact same point, which means the sun will still be in the same spot in the sky for everybody, no matter what the tilt of the Earth is. So I just didn't bother to depict it. By the way, if you still want to see the tilt of the Earth in that last illustration, just go back and watch this section of the video again, but tilt your head 23.5 degrees in some direction, just like the Earth, and then it'll be a little more scientifically accurate. You can thank me later for that one. So, I've drawn a situation here in which it is both the equinox, so the sun is shining directly on the equator, and it is solar noon. So this meridian for Emily at the equator and Nicholas at the North Pole is facing directly towards the sun. Now, these facts are incredibly important because it means that all of the geometry taking place here will happen in a flat plane. Imagine if someone were standing on the front of the Earth or the back of the Earth in this illustration. Then the sun would be at a strange angle to them in the sky, not dependent on their latitude. It would be messed up by the fact that they're, this way or this way in space. But by compressing it into a plane, which is done by doing this on the equinox and at solar noon, then the angle that the sun is in the sky depends wholly on the angle from which you're viewing it on the Earth. And in this case, it is the latitude. So, in order for this to work, it has to be solar noon and it has to be the equinox. So anyway, let's look at the situation here for Emily. Emily is at 0 degrees latitude on the equator. So I'm going to write 0 degrees here. Now, what is the angle of the sun in the sky for Emily? Well, the sun is directly overhead the point where she's standing. She's standing at the subsolar point. So the sun will be directly overhead. That is 90 degrees. Now let's look at Nicholas's situation on the North Pole. He is at 90 degrees latitude, up at the top of the world. But then how about the sun in the sky for him? Well, this illustration isn't to scale, of course. The sun is way further that way, and the Earth is way smaller than the sun. So it's not going to be exact, but it is basically going to be at the horizon. So that is 0 degrees, like this. So then, what is the formula to get from the angle of the sun in the sky to your latitude? You may see that the latitude is simply 90 degrees minus the angle of the sun in the sky. Just like that. And so all we need to do to find our latitude is wait for the equinox and solar noon, and then measure the angle of the sun at the sky, and subtract that from 90, and that's it. So as an example, let's say someone was standing right here, and they somehow did not know their latitude, yet they knew it was solar noon and the equinox, which was totally possible in the ancient times, by the way. They did that. And they knew that the sun was 50 degrees up in the sky. So then how do they tell their latitude? Well, you just take the 50 degrees, plug it into this formula, 90 minus 50 degrees, and you get a latitude of 40 degrees. Easy. Well, today, for me, is the spring equinox, and I think solar noon's in a few minutes, so let's go try. So I've got a little sunny spot in my backyard set up here. I made sure to check if this table was level, which it could be a little better, but it could certainly be a lot worse, so I think it'll do the job. Okay, my clock says it is 12:46 p.m., which means it's solar noon. It's time to make the measurement. And I've got a protractor here that I'll use to measure the angle of the sun. I'm going to be moving this part and seeing how small I can get it on the table, which means it's directly pointing towards the sun. So let's go ahead and do that. Okay, so I'm going to place the protractor in this specific position because, as you can see, we have a 0 up here and a 90 down here. If the sun is directly above us, we will get a reading of 0 degrees latitude, as if we were on the equator. So I'm simply going to read this row of numbers here instead of having to convert from the angle of the sun in the sky to our latitude. So what I'm going to do is place the protractor exactly straight up and then rotate it so that its shadow forms just a line on the table, which means it's pointed directly to the sun. And I'm simply going to move this part of it until it looks like the shadow of this rod is as small on the table as I can get it. Whoop. And it looks like we've got about 42 degrees, just under 42 degrees, which makes sense because I live just north of the Ohio State University's Columbus campus, and the 40th parallel, the 40-degree latitude line, runs right through their campus. And so I think the error towards 90 degrees is not due to being north of the campus. I don't think I'm that far north enough. It's probably just human error. But that is very close, very satisfactory. And that's how you do it. That's how you measure your latitude, using that big, beautiful, burning ball of fire in the sky. But there's one more thing I want to show you, and it's a little less direct. So another thing we can do is, I've got a Rubik's Cube here. This is a Hudong light. I know it is 57 millimeters tall. So if I place it on the table and angle it just like that, so that the sun is casting its rays directly on the edge of the cube, all I need to do is measure the length of its shadow here, which I would do with this protractor here, but it's in imperial units and I need some metric here. And then we can do a bit of trigonometry to get the angle of the sun. Quick correction. The side length of a Hudong light is actually 55 millimeters and not 57. Sorry about that, Hudong fans. Anyway, here's the situation we had outside. The sun's up here, casting a shadow of the cube onto this flat table. The cube is 55 millimeters tall, and the shadow is 46 millimeters long. So then, what do we do now? Well, because this is a right triangle, that means we can do trigonometry to this. But what angle do we want to find? Well, it turns out it's actually this one. And that's because, well, let's think about it. Imagine if the sun were straight up in the air. Then this angle would be 0. But if the sun were over here horizontally, then this angle, this won't even be a triangle anymore. This angle would be pretty much 90 degrees. So this angle is just the latitude, assuming it's solar noon on the equinox. So let's find this angle. First, let's call it theta. But then, how do we find the measure of the angle? Well, you may remember from high school math, tangent. The tangent of the angle is opposite over adjacent. So that's going to be 46 over 55. And now all we need to do is just take the inverse tangent, or arctangent, of both sides. And that gives us theta equals 0.696. Oh, I'm in radians. Format. No. Mode. There it is. All right. 39.908 degrees. That's pretty good. Remember, we're looking for 40 degrees, just like Ohio State's campus. Not quite exact because, you know, there's going to be some limitations with the width of a millimeter, but that's pretty dang good. Thank you very much, Hudong Light. And there you have it, everybody. I hope that was interesting enough. That's just something fun I like to do. The 2 times a year this happens and observe the astronomically rare day. and it's cloudy outside, which is nice that it was sunny when I was actually running the experiment. And that reminds me, if you want to try this at home yourself, don't fret if you don't do it exactly on the equinox. The results you get can't change by more than a degree every day, so if you do it on some day that's nice and sunny outside at solar noon, right around the equinox, the results should be pretty similar, so don't worry. But wait, that's not all. Wait for the summer solstice, and I'll be doing this experiment again and taking the difference between the two results, and hopefully we should be able to measure the tilt of the Earth, which I think might even be more interesting than the latitude. So stay tuned for the middle of June, the start of summer, and take care. I'll see you guys later.